Hello. Today we will talk about geometric duality and line arrangements. Let's start with a few example problems. The first problem is, given a set of points in the plane, we want to check whether 3 points lie on the same line. A naive solution here would be, of course, to check all triplets of points, and if one of them lies on the same line, then of course the answer is yes. And the running time of this algorithm would be cubic. Of course, we need to check all triplets of points, and for each triplet we can check whether they lie on the same line in constant time. Next problem. Now, instead of checking whether there are 3 points that lie on the same line, we want to find 3 points P, Q, and R, which are the corners of the smallest area triangle. Again, we can take the same approach as in the previous problem, check all triplets of points, and maintain the minimum area triangle that we've seen so far. The running time of that algorithm would be cubic. Next problem. Again, given a set of points in the plane, what we want to compute now is for every point P, the angular order of the remaining points around it. So we will have n lists of points ordered around each point. For one point, we can sort the remaining points by angle around it in n log n time, and thus in total we can produce n such lists in big O of n squared log n time. And finally, one more problem. Alice and Bob want to share a Hawaiian pizza, and we mark pineapple with yellow dots and ham with red dots. And they want to cut this pizza so that each one of them gets the same number of pineapple pieces and the same number of ham pieces. How can we find such a cut? Well, a naive approach here is again to consider all possible lines, which there will be big O of n squared of, and check if each of these lines splits the points equally. So the total running time is again cubic. We have considered 4 problems, which we may say have more or less relation one to each other. And with the brute force approach, we know how to solve each one of them in cubic or close to cubic running time. By the end of this lecture, you will know how to solve these problems and many other problems much more efficiently. And to do so, we will use the tools of geometric duality and line arrangements. In this video, we will introduce the notion of geometric duality and we will learn about some of its properties. We'll start with a plane and a system of coordinates in it, x, y, and let's consider a point P in it. And just for example, let's say that the coordinates of P are 2 and 1. Then we will construct a dual plane with the system of coordinates, let's say A and B, and in it we will define a line B equals 2a minus 1. So you see we use the x and y coordinates of the point P to create a dual line P star in the dual plane. So in general, if our point P has coordinates px and py, the dual line that we usually denote with the same label P but with a star next to it will be given by an equation y equals px times x minus py. Similarly, if we are given a line in the original plane, or what we call primal plane, we can construct, using the values of the slope and intercept, a dual point in the dual plane. The first coordinate of this point will be equal to the slope of the line, and the y-coordinate of this point will be minus the intercept of the original line. So this is all there is to the definition of the dual plane and dual points and lines in it. Now let's see what kind of properties we can derive from this definition. By applying the definition, we can prove the following properties. First, the property of self-inverse. The dual of a dual point is the point itself, and the dual of a dual line is the line itself. So if we apply the dual transformation to a given plane twice, then we will obtain the same plane and the same objects in it. The second property is that vertical distances between the points and lines in the primal plane and their dual lines and points in the dual plane are conserved. Here in the figure we have a line with the equation y equals mx plus b and its dual point L star with coordinates m and minus b in the dual plane, and the point P with coordinates px, py in the primal plane, and the dual line P star with the equation y equals px times x minus py. Now, if we want to measure the vertical distance between the primal point P and the primal line L, we need to find the y coordinate of the point on the line with the same x coordinate as P, and then the vertical distance can be found with this expression. And now if we perform the same operation in the dual plane, if we find the point on the line with the same x coordinate as the point L star and find the vertical distance between the 2 points, we will get exactly the same expression as in the primal plane. The next property is that the relation between the points and lines in the primal plane will flip when we will consider the duals of those points and lines in the dual plane. For example, if a point P is below line L in the primal plane, then the line P star will lie above the point L star in the dual plane. If a point P would lie on the line L in the primal plane, then the line P star would pass through the point L star in the dual plane. And similarly, if the point P would lie above line L, then the line P star would go below the point L star in the dual plane. Finally, two more properties. If we have lines L1 and L2 intersect in some point R in the primal plane, that means that the corresponding points L1 star and L2 star will lie on the dual line R star. And if we have 3 points Q, R, and S collinear, let's say that they lie on some line L2, that means that in the dual plane, the 3 corresponding lines Q, R, and S will pass through the same point, which will be the dual to the line L2. All of these properties directly follow from the definition of the dual transform, and I will leave this as an exercise for you to check by yourself. From the definitions of dual points and dual lines, we can also infer the dual objects of other geometric objects, for example, a line segment. So let's consider a segment S with 2 endpoints P and Q, and let's figure out what the dual to a line segment S would be in the dual plane. So here I have a segment PQ, and I want to figure out what each of the points lying on the segment between P and Q will be dual to in the dual plane. Well, by definition, a point P will be dual to some dual line P star, and a point Q will be dual to a line Q star. Furthermore, we said that the lines P star and Q star intersect in a point which is the dual to the line on which points P and Q lie in the primal plane. So what does this mean? Where do all the points between points P and Q map to? Well, consider any point T between points P and Q. The dual to point T will be some line, again passing through the same point as P star and Q star. And now if we slide the point T left or right along the segment, we will see that this line dual to T will be rotating around the common intersection point. So if we move T from point P to point Q, it will be dual to some line that spans this so-called double wedge. Indeed, here we have the lines P star and Q star, and the segment S is dual to the double wedge S star. And also observe that if we have line L intersecting the segment S in the primal plane, then this line L will be dual to some point L star in the dual plane, and this point will lie inside the double wedge that is the dual to the segment. Now let's consider this very interesting geometric interpretation of duality, which will be helpful when we try to construct dual points and lines by hand. Consider the parabola x squared over 2, and let point P with coordinates px, py lie on this parabola. Take a moment to think about the following question. What is the line tangent to the parabola at point P? Well, let's work out the detail. First, we know that the point P lies on the parabola, and thus the coordinates of the point P satisfy the equation of the parabola. Second, we know how to find an equation of a tangent line to a curve going through some point on the curve. It will be given by the following formula. Its slope is given by the first derivative of the curve evaluated at the x coordinate of the point, and its intercept we need to compute. After we simplify this, we will find that the equation is px times x plus b. Again, because this line passes through point P, if we plug in the coordinates of the point P into the equation of the line, we can derive the value of the intercept. So the intercept is equal to py minus px squared. We can now replace px squared using the first observation we made and find that b equals py minus 2py, which is simply minus py. So the line that is tangent to the parabola passing through the point P will have equation y equals px times x minus py. Notice that this is the equation of the dual line P star in the dual plane, because the slope equals to the first coordinate of px and the intercept equals to minus the second coordinate of the point P. Okay, great. So let's summarize. First, the derivative of the parabola at point P is px. The intercept is minus px squared over 2. Thus, the tangent line to the parabola passing through the point P is given by the equation px times x minus px squared over 2. And now, if we write down the equation of the dual line of P, we will find that it is given by the same equation. Okay, so P star is tangent to the parabola x squared over 2 at point P. Now, consider a point Q that lies directly below the point P. What is the dual line Q star to the point Q? Well, let's see what we can reason about Q star. Firstly, we know that the x-coordinate of Q is the same as the x-coordinate of P. So the slope of Q star will be the same as of P star. Now we need to find its intercept or find the location of the line in some other way. So which way can we reason about it? Well, we know that the vertical distances between points and lines in the primal plane correspond to the dual lines and points in the dual plane. So if we consider the point Q and the line P star as the objects in the primal plane, and the line Q star and the point P as the objects in the dual plane, then we know that the vertical distance will be preserved. So the vertical distance between Q and P star is the same as the vertical distance between P and Q star. And now we need to figure out, does the line Q star lie above point P or below point P? And for this we can use the other property that we have shown, which is the relation between points and lines in the primal plane gets swapped between the dual lines and dual points in the dual plane. So if Q lies below the line P star in the primal plane, then the line Q star will lie above the dual point P in the dual plane. Indeed, Q star has the same slope as P star, vertical distances are preserved, and because of the relations between points and lines are swapped in the dual plane, Q star lies above point P. Now, if we consider the point Q prime, which is directly above point P that lies on the line Q star, what is the dual to the point Q prime? Well, by symmetry we can find that the dual line Q prime star passes through the point Q and again is parallel to the lines P star and Q star. One final observation that we can make here is that only the points on the parabola will have their dual lines passing through them. And to find these dual lines, we can simply find the tangent line to the parabola through the given point. Now, let's see how we can use duality to solve the problems that we have started with and many other problems. But before that, let me introduce one more definition. The lower envelope. Consider a set of lines in the plane. The lower envelope is the set of points from these lines that do not have any other line passing below it. So in green here is denoted the lower envelope of the lines, and what I'm drawing is that from every point on this lower envelope, if I draw a vertical ray downwards, it will not intersect any of the lines. Now let's see how we can compute a lower envelope given a set of lines. And of course, because we are using duality, let's see if we can convert this set of lines into a set of points and solve the dual problem on that set of points. So if we have a set of lines in the primal plane, we will have a set of dual points in the dual plane. Let's answer the question of which lines support the segments of the lower envelope. In particular, Let's consider some segment with endpoints P and Q. Assuming that the points P and Q lie on the lower envelope, that means that there are no lines from the input set of lines that lie below P and Q. Now, in the dual plane, that means that there are no points lying above the dual lines P star and Q star. Moreover, the point P lies on the line L of the input set of lines that also passes through the point Q, but also on some other line. That means that the dual line P star will pass through the point that is dual to L, L star, and some other point dual to the other line. Similarly, line Q star passes through the point L star and some other point that is dual to the line that is also passing through the point Q. So now what does this mean? That there are no points that are dual to the original lines lying above Q star or lying above P star. Well, that means that the lines Q star and P star define the edges of the convex hull around the point set. And in particular, they define the edges of the upper hull of the set of points that are dual to the set of lines in the primal plane. The vertex of the upper hull, L star, corresponds to the line L in the primal plane that passes through the points P and Q. Thus, we can conclude with the following lemma. The lines of the lower hull, if we are considering them in the order from right to left, will correspond to the vertices of the upper hull in the order from left to right. So we can conclude that we can compute intersection of half spaces, which is the lower envelope of a set of lines, by computing a convex hull on the dual set of points, and vice versa. Indeed, duality can provide us with a new perspective on how to solve a given problem. If we are given a problem on a set of lines L, we can convert this problem into a dual problem on a set of points L star. And an example of such a problem we have just seen when we want to compute an upper or lower envelope on a set of lines, and instead of solving it directly on these lines, we convert this problem to have a set of points as the input, and instead of finding the lower envelope or an upper envelope in the primal plane, we find a convex hull, an upper hull or a lower hull in the dual plane. And because we already know how to find a convex hull of a set of points, we converted the original problem, which we didn't know how to solve, to something that we already have a lot of algorithms developed for. Now let's see if we can make use of the duality transform in the opposite direction. If we are given a problem on a set of points, let's see how we can convert this problem into a dual problem on a set of lines and hopefully make some new observations that will give insight into the original problem. Now, when we will have a problem on a set of lines, we will want to compute some data structure on it, and this will be what we call an arrangement of lines.